today we will discuss a very important concept, that how we can estimate the average stock return by using the concept of confidence interval. We will discuss in detail that what is confidence interval and how you can apply it in a practical data using stock data of Microsoft. Let us start. Last lecture you have studied population and sample, and in the lab of last lecture we studied about variation of sample. Today we will discuss about confidence interval in a little detail, and after discussing it we will do some practical about confidence interval. This lecture is very important and you have to listen it carefully in order to get the complete idea about confidence interval. So this is the best example I have got from the internet, and let us start listening.
Understanding confidence intervals. In order to understand confidence intervals, we need to understand sampling and sampling error. To find things out about a population of interest, it is common practice to take a sample. A sample is a selection of objects or observations taken from the population of interest. For example, a population might be all apples in an orchard at a given time. We wish to know how big the apples are. We can't measure all of them, so we take a sample of some of them and measure them. To find out about different sampling methods, see our video, Sampling, Simple, Random, Convenience, etc. Inference is when we draw conclusions about the population from the sample. Because the sample is only a selection of objects from the population, it will never be a perfect representation of the population. Different samples of the same population will give different results. This is called sampling error or variation due to sampling. There will always be sampling error. Confidence intervals. When we express an estimate of a population parameter, it is good practice to give it as a confidence interval. A confidence interval communicates how accurate our estimate is likely to be. Say we wish to find out how big the apples are in our orchard. We put this as an investigative question. What is the mean weight of all the apples in the orchard? We take a sample and calculate the sample mean. This is the best estimate of the population mean. We use a confidence interval to express the range in which we are pretty sure the population parameter lies. In this case, the population parameter is the mean weight for all the apples in the orchard. What affects the width of confidence intervals? The width of a confidence interval depends on two things: the variation within the population of interest and the size of the sample. Variation in the population. If all the values in the population were almost the same, then our sample will also have little variation. Any sample we take is likely to be pretty similar to any other sample. Our estimate is going to be pretty close to the true population value. We would have a small confidence interval. But a more varied population will lead to a more varied sample. Different samples taken of the same population will differ more. We would be less sure that the sample mean was close to the population mean. Our confidence interval would be larger. So, greater variation in the population leads to a wider confidence interval. Sample size also affects the width of a confidence interval. If we take a small sample, we don't have much information on which to base our inference. Small samples will vary more from each other. There is more variation due to sampling or sampling error with a small sample. In larger samples, the effect of a few unusual values is evened out by the other values in the sample. Larger samples will be more similar to each other. The effect of sampling error is reduced with larger samples. When we take a large sample, we have more information and can be more sure about our estimate. The confidence interval can be smaller. There are several methods for calculating confidence intervals: informal, traditional normal-based formulas, and bootstrapping. When we use traditional confidence interval formulas, the stated level of confidence also affects the width of the confidence interval. All estimates of population parameters, such as means, medians, differences of means and differences of medians, should be expressed as confidence intervals. You can learn more about how to calculate confidence intervals in our other videos.
Hope you have got the very clear idea, and we will discuss some mathematical representation of confidence interval. And after discussing mathematical representation, we will move towards stock data and talk about the implementation of the confidence interval. So let us move towards the second video and check it carefully.
StatQuest. 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 Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today's StatQuest is all about confidence intervals. You may have seen or heard of confidence intervals before. However, if you're not very confident about them, then you're not alone. Many people misunderstand confidence intervals, but that's only because they didn't learn about bootstrapping first. Now, just to clarify, there are lots of ways to calculate confidence intervals, and bootstrapping is just one of them, but for me, it makes it easiest to understand. But when you see confidence intervals out there in the wild, you're likely to see a different way to calculate them. Now, even though we just did bootstrapping, your brain might be a little cloudy and you may have forgotten what it was all about. My brain's like that, so I totally understand. That's why we're going to do a little bootstrap refresher. Imagine we weighed a bunch of female mice. In this case, we weighed 12 of them. We didn't weigh every single female mouse on the planet, just 12. Now, we can take these 12 measurements and we can use them to calculate the sample mean. Now, the sample mean is not the mean for all mice in the entire planet. It's just the mean of the mice that we sampled. However, we can use bootstrapping and the data that we have here to determine what values would be reasonable for the global worldwide mean of all female mice on the planet. Now that we've calculated the sample mean, we can bootstrap the sample. To bootstrap the sample, we randomly select 12 weights from the original sample, and duplicates are okay. Here's an example of a bootstrapped sample. We can see that this measurement on the far left was sampled twice in our bootstrap sample, and the measurement to its right wasn't included in our bootstrap sample. This is called sampling with replacement. Now we calculate the mean of the random sample. After we've calculated the mean of our first random sample, all we have to do is repeat steps 1 and 2 until we've calculated a lot of means, sometimes more than 10,000. And here's what it looks like when we've calculated a lot of means. It's maybe a little fewer than 10,000, but you get the idea. Anyway, that's all there is to bootstrapping. Now let's talk about confidence intervals. Usually when you see a confidence interval out in the wild, it's called a 95% confidence interval. A 95% confidence interval is just an interval that covers 95% of the means. So here we have a black bar that spans 95% of the bootstrapped means that we just calculated. That's it. That's all a confidence interval is. Nothing more, nothing less. Can you guess what a 99% confidence interval is? Here's a hint. It's wider than a 95% confidence interval. Alright, I'll tell you. It's just an interval that covers 99% of the means that you calculated when you bootstrapped the sample. Now that we know what confidence intervals are, we might ask, why are they useful? Well, I think confidence intervals are useful because they are statistical tests performed visually. Because the interval covers 95% of the means, we know that anything outside of it occurs less than 5% of the time. That is to say, the p-value of anything outside of the confidence interval is less than 0.05, and thus significantly different. Here's an example of a visual statistical test. You'll remember we originally calculated the sample mean. The sample mean is an estimate of the true mean for all female mice. Well, with our confidence interval, we can figure out what the p-value is that the true mean of all female mice, not just of our sample, is less than 20. To perform that test, we draw our confidence interval, which we know because of bootstrapping or some formula that we use. We can see that the area left of 20, so values less than 20, are outside of our 95% confidence interval. Because the highlighted region is outside of the 95% confidence interval, which contains 95% of the means, we know that the probability that the true mean is in this area has to be less than 0.05. Thus, the p-value is less than 0.05. This is unlikely, and because of this, we can say there's a statistically significant difference between the true mean and any value less than 20. Here's another example of a visual statistical test. In this case, we're going to compare two samples. Here, we've weighed female mice, and now we have a sample of male mice. We've already done the bootstrapping on that sample, and here in the figure, we just show the means from that bootstrapping. Because the 95% confidence intervals do not overlap, we know that there is a statistically significant difference in the weights of female and male mice. That is to say, we know that the p-value is less than 0.05 just by looking at the picture. There is one caveat to that, and to illustrate that caveat, I've shifted the means a little bit over to the left so that now the confidence intervals overlap. If the confidence intervals overlap, there's still a chance that the means are significantly different from each other. So, in this case, you still have to do the t-test. But when the confidence intervals do not overlap, then you can rest assured that there's a statistically significant difference between those two means. That's all there is to it. Tune in next time for another stat quest.
Work on understanding the mathematical concept of confidence interval and bootstrapping. I hope that you are clear with the idea. And what we have discussed in the above two videos, if the sample is a good representation of the population, then the mean of the sample is always close to the population mean. Our objective is to estimate our population between the lower limit and the upper limit. Let us see some video of stock distribution of stock data and confidence interval. But before checking the video, I want to tell you that whenever we are working on stock data, and we have also discussed in the last lecture, that whenever we are working on the data of stock, our priority is to standardize the data before applying or checking the confidence interval. So there is a concept of Z distribution. Basically, we normalize our distribution of data, which is the normal distribution, to Z distribution. Why we do Z distribution? Because we want to standardize the readings of normal distribution. So every time we worked on a lot of numerical of Z distribution, but this time there is a time we will discuss that what basically is the concept behind Z distribution. So let us start from the video of Z distribution. It is a very wonderful video and it will clear all the concept of Z distribution. So before going towards this types of quantiles, I want to show you what is Z distribution. Then we will move towards the stock data and talk about it in a practical. So let us start from the video of Z distribution.
In this video, we'll be learning about z-scores and standardization. By learning about both of these topics, you will learn how to calculate exact proportions using the standard normal distribution. What is the standard normal distribution? The standard normal distribution is a special type of normal distribution that has a mean of 0 and a standard deviation of 1. Because of this, the standard normal distribution is always centered at 0 and has intervals that increase by 1. Each number on the horizontal axis corresponds to a z-score. A z-score tells us how many standard deviations an observation is from the mean mu. For example, a z-score of -2 tells me that I am 2 standard deviations to the left of the mean, and a z-score of 1.5 tells me that I am 1.5 standard deviations to the right of the mean. Most importantly, a z-score allows us to calculate how much area that specific z-score is associated with, and we can find out that exact area using something called a z-score table, also known as the standard normal table. This table tells us the total amount of area contained to the left side of any value of z. For this table, the top row and the first column correspond to z values, and all the numbers in the middle correspond to areas. For example, according to the table, a z-score of -1.95 has an area of 0.0256 to the left of it. To say this in a more formal manner, we can say that the proportion of z less than -1.95 is equal to 0.0256. We can also use the standard normal table to determine the area to the right of any z value. All we have to do is take 1 minus the area that corresponds to that z value. For example, to determine the area to the right of a z-score of 0.57, all we have to do is find the area that corresponds to this z value and then subtract it from 1. According to the table, the z-score of 0.57 has an area of 0.7157 to the left of it. So 1 minus 0.7157 gives us an area of 0.2843, and that is our answer. The reason why we can do this is because we have to remember that the normal distribution is a density curve, and it always has a total area equal to 1 or 100%. You can also use the z-score table to do a reverse lookup, which means you can use the table to see what z-score is associated with a specific area. So if I wanted to know what value of z corresponds to an area of 0.8461 to the left of it, all we have to do is find 0.8461 on the table and see what value of z it corresponds to. We see that it corresponds to a z value of 1.02. The special thing about the standard normal distribution is that any type of normal distribution can be transformed into it. In other words, any normal distribution with any value of mu and sigma can be transformed into the standard normal distribution where you have a mu of 0 and a standard deviation of 1. This conversion process is called standardization. The benefit of standardization is that it allows us to use the z-score table to calculate exact areas for any given normally distributed population with any value of mu or sigma. Standardization involves using this formula. This formula says that the z-score is equal to an observation x minus the population mean mu divided by the population standard deviation sigma. So suppose that we gathered data from last year's final chemistry exam and found that it followed a normal distribution with a mean of 60 and a standard deviation of 10. If we were to draw this normal distribution, we would have 60 located at the center of the distribution because it is the value of the mean, and each interval would increase by 10 since that is the value of the standard deviation. To convert this distribution to the standard normal distribution, we will use the formula. The value of mu is equal to 60 and the value of sigma is equal to 10. We can then take each value of x and plug it into the equation. If I plug in 60, I will get a value of 0. If I plug in 50, I will get a value of -1. If I plug in 40, I will get a value of -2. If we do this for each value, you can see that we end up with the same values as the standard normal distribution. When doing this conversion process, the mean of the normal distribution will always be converted to 0, and the standard deviation will always correspond to a value of 1. It's important to remember that this will happen with any normal distribution no matter what value the mu and sigma are. Now, if I ask you what proportion of students scored less than 49 on the exam, it is this area that we are interested in. However, the proportion of x less than 49 is unknown until we use the standardization formula. After plugging in 49 into this formula, we end up with a value of -1.1. As a result, we will be looking for the proportion of z less than -1.1. And finally, we can use the z-score table to determine how much area is associated with the z-score. According to the table, there's an area of 0.1357 to the left of this z value. This means that the proportion of z less than -1.1 is 0.1357. This value is in fact the same proportion of individuals that scored less than 49 on the exam. As a result, this is the answer. Let's do one more example. When measuring the heights of all students at a local university, it was found that it was normally distributed with a mean height of 5.5 feet and a standard deviation of 0.5 feet. What proportion of students are between 5.81 feet and 6.3 feet tall? Before we solve this question, it's always a good habit to first write down important information. So we have a mu of 5.5 feet and a sigma of 0.5 feet. We are also looking for the proportion of individuals between 5.81 feet and 6.3 feet tall. This corresponds to this highlighted area. To determine this area, we need to standardize the distribution, so we will use the standardization formula. Plugging in 5.81 to this formula gives us a z-score of 0.62, and plugging in 6.3 into the formula gives us a z-score of 1.6. According to the standard normal table, the z-score of 0.62 corresponds to an area of 0.7324, and the z-score of 1.6 corresponds to an area of 0.9452. To find the proportion of values between 0.62 and 1.6, we must subtract the smaller area from the bigger area. So 0.9452 minus 0.7324 gives us 0.2128. As a result, the proportion of students between 5.81 feet and 6.3 feet tall is 0.2128. If you found this video helpful, consider supporting us on Patreon to help us make more videos. You can also visit our website at simplelearningpro.com to get access to many study guides and practice questions. Thanks for watching.
To explain some single things and simple things about Z distribution. You can see there is a population and there is a graph in the population in front of you, and these are two quartiles of distribution. You can see on the right hand there is a different color and on the left hand there is a different color. I want to explain it. If someone is talking about the confidence interval, let me draw something here. Here is some normal distribution or close to a normal distribution. There is a curve about the distribution of data. If someone is talking about the confidence interval of 80%, so you have to do like this. 1 means you can say 100, and 0.80, if I write here 0.8, so there is an answer of 0.2. So if someone is talking about the confidence interval of 80%, so 20 is, remains 1 minus 80. So how would you distribute it? The simple way to distribute it is to divide this 2 by 2, means making half of it and distribute 10% here from this end and 10% here at this end. You can color it as a red color and you can color it in red color, and this area is the confidence interval of 18%. So whenever we do programming and finding the confidence interval of calculating our mean or calculating the average return, we will find a confidence interval in a similar way. So that's all for your explanation, and I am hopeful that before finding confidence interval you have to do Z distribution, and you are 100% sure what is Z distribution and how it came into being and how the concept is generated. Now before ending this lecture, I want to go towards the practical lecture of confidence interval and hypothesis testing. So I am opening my code in front of you, and we will see the practical concept of all the videos we have discussed in confidence interval in the form of practical, and this practical is applied on the stock data, so you will understand all the concepts behind it. So after population, variation of sample, we have discussed confidence interval, and this is so much related to the previous lecture of variation of sample, and you have seen these things in the videos as well. There are libraries, we have imported the Microsoft data, and we have calculated the log return, and we have already calculated log return in the last videos as well. It is saying that there is no file named as Microsoft, so we can call the file because we have the file. Basically we have to copy this file here and place it in the same folder, or we can give it the path as well. So that's a little bit of mistake. Downloading libraries, you can see there is a file and log return, and after log return we are calculating the sample size, the sample mean, and the sample standard deviation. Now for the quantile, you can see norm.ppf is a command for finding quantile, and if you are finding the 80% confidence 90% confidence interval, I have already told you in the paint how you can find it. You can see norm.ppf 0.9, 0.1, 0.9. Okay, and we are finding the interval of the left by summing the sample mean with the z left multiplied by standard deviation. It is a simple formula, and the interval of right, and you can calculate the confidence interval, and you can see the confidence interval is positive. Here is our answer, and 90% confidence interval will tell you that there is a 90% of chance that the average stock return lies between left interval and the right interval, and you can see we have find the values as well. I hope that you have understand the concept of confidence interval and got a lot of things according to it, and we will discuss it more in the next videos.